Here, we are going to solve for the eigenvalues, eigenvectors, and eigenspaces of this given 3 by 3 matrix using this characteristic equation that we're able to solve in the previous video. Please review that video as to how do we come up with these 3 binomial expressions here. The goal for this first is for eigenvalues by solving for the lambda symbols here. We can do that by treating this equation equal to 0, and then this is only true if 1, 2, or even all of these binomials are equal to 0. Hence, we are going to equate them one by one to 0. We have lambda minus 4 equals 0. Lambda minus 1 equal to 0. So our first lambda is positive 2. Our second lambda is positive 4. And our third lambda is positive 1. These are the 3 eigenvalues of this given 3 by 3 matrix. To solve for the eigenvector, let us start reviewing this form of matrix where we are going to multiply lambda to I. In this case, our I is the identity matrix for 3 by 3 matrix. So you have 0, 0, 1 here. Okay? And then that would mean we're going to multiply lambda to 1, 0, 0, 0, 1, 0, 0, 0, 1 minus your matrix A, 2, negative 2, 3, 0, 3, negative 2, 0, negative 1, and then positive 2. Continue. Let's have here lambda 0, 0, 0, lambda 0, 0, 0, lambda minus 2, negative 2, 3, 0, 3, negative 2, 0, negative 1, and then positive 2. Since they are both 3 by 3 matrices, so our difference is defined, and we'll have these entries. We have lambda minus 2. 0 minus negative 2 is positive 2. 0 minus 3 is negative 3. Then, you have 0 minus 0, lambda minus 3. Next, you have 0 minus negative 2 is positive 2. You will have 0 minus 0, 0 minus negative 1 is positive 1, and you have lambda minus 2. Right? This matrix now will be subjected into this process, multiplying a certain vector here and equating the result to the 0 vector. This x would be the vector in R3, x sub 1, x sub 2, and x sub 3, which will correspond to the eigenvector of a specific eigenvalue that you're going to substitute in this form. And of course, 0 would be a 0 vector on R3, which is 0, 0, and 0. So we'll have this form as this. So using the first lambda, this would be, since our first lambda is 2, so 2 minus 2 is 0. You have 2, negative 3. This is 2, I mean 0. 2 minus 3 is negative 1. You have here 2. And you have 0, 1, and 0 here because 2 minus 2. Okay, multiplying that to x sub 1, x sub 2, and x sub 3 equal to this here, 0, 0, 0. Now, in solving for the values of x sub 1, x sub 2, and x sub 3, of course, you could apply different methods here, but one of which is very unique already, just by analysis. If we're going to multiply all these 3 rows to this, you will always receive an x sub 1 here, which is non-existent, because you have 0 x sub 1 plus 2 x sub 2, okay? So we'll have here plus 2x sub 2 minus 3x sub 3. On the second row, you will still have 0x sub 1. And for the third row, you will still have 0x sub 1. What does this mean? Your x sub 1 can take any value. So we're going to let here x sub 1 be equal to an arbitrary variable t. Okay? So since it's already t, let me remove this and continue with the rest of the process now. But I'm going to jump in the third row as I have here. Of course, 0 times x sub 1 is 0 x sub 1. You will have x sub 2. Then 0 times x sub 3 is also is also 0. So you have here a result of x sub 2, which is automatically equal to 0. That would mean, using the second row, I have here 0 x sub 1, you have negative x sub 2, and you will have here plus 2 x sub 3. We're going to use this to solve for our x sub 3, but since x sub 2 is already 0 given here, so you have 2x sub 3 is equal to 0, our x sub 3 is now equal to 0. So these are the three values for the comprising the first eigenvector, which is corresponding to our eigenvalue, which is 2. So our eigenvector x, that's x, let me make this thicker, is equal to, or x sub 1 is t, 0, and 0 here. Factoring t, we have 1, 0, 0. This is our eigenvector now. We have 1, 0, and 0. So in short, our eigenspace is set of t times 1, 0, 0, such that t is an element of R but not an element of a set containing 0. So you have here your eigenspace. This is your eigenvector for your eigenvalue, which is 2. Again, it's very important that you were able to use the correct analysis, as here we have a column with zero entries. This would mean that the corresponding value, which is in this case x sub 1, is automatically equal to 0. So you just simply need to review that, or of course take a stand on your analysis so that you're able to come up with this. And then of course again, you can jump to our third row because you only have one entry, which is non-zero here, and with that we're able to come up with x sub 2, which is 0, and use that to solve for our x sub 3. But we are not done yet because we still have two more eigenvalues. This would mean we also have another eigenvectors corresponding to them. So let's start with our next eigenvalue, which is 4. So you will have here an eigenvalue which is 4. This was the same expression earlier of your lambda I minus a. So substituting 4 there, you will have 4 minus 2 is 2, 2 negative 3, 0, 4 minus 3 is 1, you have 2, 0, 1, 4 minus 2 is also 2. Notice here that we have two rows of the same entries. So in previous analysis before, we can actually treat this as entire row of 0. But of course, let's just simply continue. X sub 1, x sub 2, and x sub 3 here. So this is equal to 0, 0, and 0. So again, there are a lot of processes that you can do here. Earlier, we're able to use analysis. Here, we could also even use analysis here as mentioned. But just to illustrate this new other method, let us try to come up with the row echelon form of this. So that would mean we're going to divide or multiply 1/2 to the entry on R1. So this we will have a leading 1. Okay, for new R1. Okay, so this would become 2 divided by 2 is 1, 1, then negative 3 halves. This is still 0, 1, 2. This is 0, 1, 2. Next is to make this 0, so that we will have here the form of the row echelon form. So you will have negative 1 on R2 plus R3 for a new R3. You'll have this result. Sorry, this is still 1, 1, 2, negative 3 halves. 0, 1, and 2. 0. Negative 1 times 1 plus 1 is 0. Negative 1 times 2 plus 2 is 0. This is what I meant earlier, that one of the rows here is actually a row of zeros. With this, we're going back to the product of multiplying this to x sub 1, x sub 2, and x sub 3. We can see a row that we don't have any other entries here aside from 0. This automatically means that your x sub 3, okay, can be represented by an arbitrary constant. Since we use here a t earlier, so we'll use here s. Okay, and with that, for our second row, we will have, if you're going to multiply this with this, you have 0x sub 1, you have x sub 2 plus 2x sub 3 equals 0. But x sub 3 is already s. So x sub 2 plus 2s is equal to 0. Okay? And then you will have here x sub 2 is equal to negative 2s. Then we will go to our first row. So you have 1 times x sub 1 is x sub 1 plus x sub 2 minus 3 halves of x sub 3 equal to 0. This is s. This is minus 2s. So x sub 1 plus negative 2s plus, minus 3 halves s is equal to 0. So you have x sub 1, that's negative, so that's negative 4 halves. So negative 7 halves of s equal to 0. So x sub 1 is positive 7 halves of s. With all of this, since our eigenvalue here is 4, okay, its corresponding eigenvector can be shown in this manner. So you have your eigenvector here, your entries, x sub 1, 7 halves of s, x sub 2 is negative 2s, and our x sub 3 is s. Factoring s, you have 7 halves, negative 2, and then 1. This is your eigenvector. And writing a set for all values of s times 7 halves, negative 2, and 1, such that s is an element of R, but not an element of a set containing 0. This is your eigenspace, eigenvector of your eigenvalue, which is 4. So, going to our last one, you have lambda sub 3, your third eigenvalue, which is 1. Okay? Which is 1 here. So, this is still the form. Substituting 1 there. 1 minus 2 is negative 1. 2, negative 3. 0. 1 minus 3 is negative 2. 2. 0, 1. 1 minus 2 is negative 1 as well. So, again, this would be multiplied by x sub 1, x sub 2, and x sub 3 is equal to 0, 0, and 0. Let's use the same process earlier. Let's come up with the row echelon form of this by first multiplying negative 1 to row 1 to have a new row 1, so that this would be a leading positive 1. This would mean I have this form, positive 1, negative 2, and then positive 3. 0, negative 2, and 2, 0, 1, negative 1. Okay. Now let's try to make this in the form of 1. So we're going to multiply negative 1 half to row 2 for a new row 2. Hence, we will have 1, negative 2, 3, 0, that's positive 1. You have negative 1 here, 0, 1, negative 1. Notice, same as earlier, you have here rows of the same entries. So you're expecting that 1 is already an arbitrary constant, or even you will come up with the row of 0 here. But to illustrate, let's try to multiply negative 1 to R2 plus R3 for a new R3. So our final form is 0, not 0, 1, negative 2, 3, 0, 1, negative 1, 0, negative 1 times 1 plus 1, 0. Negative 1 times negative 1 is positive 1 plus negative 1, 0. So again, x sub 1, x sub 2, and x sub 3 here. Your x sub 3, okay, let us make this equal to w, another arbitrary constant. Using that for our second equation, you have x sub 2 minus x sub 3 is equal to 0. X sub 2 minus w equal to 0. X sub 2 is w. Let's separate this, by the way. Okay. And then for our first, you will have x sub 1 minus 2x sub 2 plus 3x sub 3 is 0. X sub 1 minus 2, our x sub 2 is w, plus 3, w as well. Okay, so we'll have here x sub 1 plus w equal to 0. So our x sub 1 is negative w. Alright? So our eigenvector For our eigenvalue, which is equal to 1, you'll have negative w, w, and w. Factoring w, you will have 1, rather negative 1, 1, and then 1. In set form, you will have w times negative 1, 1, and 1, such that w is an element of, oh sorry, my bad. Let's make it here. Element of R, but not an element of the set containing 0. This is your eigenspace, the third eigenspace. Pardon with that. This is your eigenspace for your eigenvector, for your eigenvalue, which is 1. So again, analysis, proper operations, including your row echelon form. But we started with our characteristic equation, getting our eigenvalues, and using this notation. Thank you very much for watching.